Hello, everyone. Welcome to my talk about our paper accepted by APPROX 2022, which is entitled Ordered K-Meeting with Outliers. My name is Shichuan Deng, and this is a joint work with Qianfan Zhang. Now I'm an engineer at Alibaba Group, and Qianfan Zhang is a graduate student at Princeton University. And the work of this paper is done while we were both students at IIIS of Tsinghua University. So first, let's have some background before we discuss the definitions and the algorithms of this problem. So what are clustering problems? There are usually two perspectives in understanding these problems. The first is called the non-centroid based clustering problems. For example, in this picture, on this land, we are trying to divide them into different groups so that we can plant different kinds of crops on them, and which will minimize the efforts we need to put in to organize them. And for this kind of problems, they are for each cluster, there are no sort of designated centers for each of them. And for the second kind, called centroid-based clustering problems, we consider these points to be clients that are connected to the facilities, which can provide service to these clients. And in this rough example, the seeds of the dandelions are connected to the sprouts so that they can maximize the reproduction capabilities. And here's a more abstract example called the K-means problem, which is one of the most famous problem in real-world clustering. So in the input, we are given a set of points in Euclidean space, and our goal is to cluster them into at most k clusters. And the objective is to minimize the sum of squares of distances from each point to its cluster mean. And here, the cluster mean of a certain client, the cluster mean of a certain cluster is just the average of their coordinates, because we are clustering points in a vector space. And it has been shown that k-means, or more precisely, continuous Euclidean k-means in this case, because we are allowing the center of each cluster to be just the average, whichever that point is. And so this problem has shown to be APX hard, which means that as an optimization problem, it is very hard to approximate this problem very well. So we cannot approximate them within an arbitrary accuracy. So in other words, there are no p-tases for this problem. And there are also various inapproximability results for continuous Euclidean k-means. For example, it has been shown that it is impossible to approximate this problem within a factor of 1.06, which is based on the assumption that p is not equal to np. And on the positive side, there's a very recent paper showing that this problem admits a 6.12903 approximation. So we can see that the study of approximability of these clustering problems is still an ongoing and active field of research. Meanwhile, there are also more quote-unquote modern clustering problems. Among them, there are usually two approaches we can take. First, we can look at these problems where more general constraints are put on the facilities or centers we are choosing. For example, the famous knapsack center problem and the matroid center problem. On the other hand, one can also look at more classing criteria or classing objectives. For example, the famously known ordered k-median problem and the robust k-median problem. Now onto the definition of the problem we are specifically interested in this paper, which is called ordered k-median with outliers, aka robust ordered k-median with outliers. In the input, we are given a set of clients and a set of facilities that are both in a common metric space. We also have two integers m and k. And finally, we're given a non-negative, non-increasing vector, w, which has dimension m. And the goal is to open k facilities and select m clients that are considered served here. Then we need to assign an open facility for each served client, which will give us a vector called C, in which each entry is just the distance from each served client to its assigned facility. And for this vector C, the ultimate goal of this optimization problem is to minimize W transposed times C down arrow. So C down arrow here actually means that we sort the entries of C in non-increasing order as well. So here both W and C down arrow are both they are both non-increasing. So after seeing the definition, one may wonder why we are using this objective. For some of you that are familiar with ordered k-median, you might see a connection there. And before we try to look at the objective more carefully, we can rephrase it in another way. So equivalently, we can, because instead of connect only m clients, we can connect all of them and use another vector called W0 here. So we can consider W0 as a replacement for W, the weight vector called the weight vector. So in W0, all the entries are before the last m are zeros, and the last m possibly non-zero entries are non-increasing and non-negative. So by phrasing the objective in this way, we can directly compare the problem of a robust ordered k-median with some previously studied problem. For example, robust k-center, robust k-median, and ordered k-median. And I won't go into the precise definitions of these problems here, but we can visualize the connections and differences between their objectives using the figures on the right. So in robust k-center, the weight vector is a so-called one-hot vector where all but one entries are zero, and there is only a single one. Then in robust k-median, all the entries before the last m are zeros and the last m are ones. Then in ordered k-median, the entries of the weight vector are sorted in non-increasing order. And finally, in our problem, all entries before the last m are zeros and the last m are non-increasing. So we can see that our objective easily generalizes these previously studied problems. And further, we are more interested in another problem called unimodal ordered k-median, which is even more general than the objective we study here. So in that problem, we can consider weight vectors that are first non-decreasing, then after a specific index will become non-increasing. So right now, our techniques are not sufficient to solve that problem. So we are hoping that the techniques we develop in this work will help solve that more difficult problem in the future. And now let's on to the approximation algorithm we propose for this problem in this paper. So first, we can notice that the ordered objective is a highly nonlinear objective. What I mean by highly nonlinear is not that it's nonlinear in terms of the letter vector here. So one can actually show that if we consider the letter vector as the input, this function is actually a norm. So it is indeed linear in terms of the entire vector. But if we consider the individual entries in this objective, the contribution the coefficient of contribution they have depends on the location after they are sorted in non-increasing order. So the coefficients are highly nonlinear. So to tackle this problem, there are some recent results showing that instead of directly attacking this objective, we can actually guess a function called f and replace the objective using the sum of f of the distances from each client to its assigned facility. So because it's a sum, it is arguably much easier to deal with. So we can just replace the objective using this sum. And by doing that, we only lose a multiplicative factor of 1 plus epsilon if we solve the new problem and use that solution directly as a solution for the original. And I should also mention that the complexity of guessing this function will be exponential in 1 over epsilon. But even if we use this advanced technique, we are still faced with another problem because this function only addresses the ordered objective, the inner product here, but there are also outliers, which are clients that are not selected in the final solution. So by using a previously result by this paper, we can show that the natural LP relaxation still has an unbounded integrality gap, which is sort of inherited from robust K-median. So to tackle this issue, we actually use a slightly different objective in our algorithm. So we choose a small constant lambda, and we put lambda in the input of f as well. So we solve the new problem where the objective is replaced with this lambda scaled version, and then we use that solution as an approximate solution to the original problem. And so these are the main contributions of our paper. And we also show that the approximation factor will be proportional to the reciprocal of lambda. And ultimately, this will give us a factor of 127. So this is the overall approximation factor of our algorithm. And of course, because the approximation factor is proportional to 1 over lambda, one wants lambda to be as big as possible. But it turns out, due to the techniques used in this algorithm, we can only choose lambda that are as large as around 0.0088. So which will give us a factor of more than 100. And so in effect, we marry the techniques used for solving ordered k-median, which is this f function here, and a so-called iterative rounding algorithm in this paper, which is used for approximating robust k-median. And the main contribution of our paper is to show that these two seemingly unrelated algorithm can be combined together, and we show how the reduction gives the approximation factor of 1 over lambda. And we also should note that Awad and Sergeyev in their paper also used a similar technique by scaling the distances, but they only obtain a logarithmic factor. So we not only solved a much harder problem here, we also tighten up their analysis to give a constant factor. Here is a list of references I used in the slides. And I want to thank you all for watching, and I'm looking forward to seeing you at the online venue.